So in this video, I'd like to look at a problem of an object sliding down an incline. And basically, I'm going to be applying the same set of rules as before. So basically, draw a diagram, do a free body diagram, do a sigma f equals ma, and then finally break up the components into sigma f and then solve for the equations for the unknowns. So anyway, so let's imagine that we have an incline. So here's my diagram. So it might be a word problem, but the diagrams, I'm drawing the diagram number one. So step number one, draw a diagram. We have a mass, here it is, m, and this mass, assume it's down an incline. The incline is said to be at an angle theta, so let's put up some numbers. So let's assume that this is 30 degrees and the mass is 10 kilograms. Okay, so we're going to assume that it's a slippery slope where there's no friction. So we haven't covered friction yet, so we'll be just doing just a mass, and so repeat this process over and over again of general problem solving. So we draw a diagram. So step number one is done. We have drawn a diagram and roughly put a little mass, and it's moving straight down. And I'd like to calculate the unknown acceleration a. So there's an acceleration, that thing is slowly speeding up as it goes down the incline. I'd like to know what that acceleration is. So we've done the diagram. So next is we do a free body diagram. So our free body diagram, here's a little circle representing mass number m. And we look at all the forces acting on that object. Well, there's a normal force acting on it. That is the force that's perpendicular to the surface. We'll label it as n. And if you put an angle, this normal force like this, if this angle is theta, then this angle that's between the vertical and the normal force, right, must also be theta. So this is theta also. And then there's a force of gravity pulling straight down. These are the only two forces that I can see that would apply to a mass that's sliding down a hill on an incline of theta. So we're told theta is 30 degrees. So next step, we'll have to write the sum of all forces. So I'll write that as sum of all forces acting on this object is equal to mass times the acceleration of this object. Notice a is the acceleration down, it's the magnitude, but not, so this is the vector a. Then we substitute all the forces in. So here is the normal force plus the force of gravity is equal to mass times acceleration. So next we'll have to write down the components. So n is now at an angle. So now before we do this, we have to make sure that in our diagram, right, we're actually going to select that whenever I use the symbol I, it means to the right, and the symbol J is going to mean up. So our normal force, what's the direction of the normal force? Well, I don't know what the magnitude of n is. We'll just call it n. But I know that the component that's along horizontally in the right direction is positive, and the ratio of this side to this side is called sine of this angle theta. So this must be n sine theta. And it's going to the right, so that's the I component. But this vector going upright has a up component, and this is your j component. This will be the ratio of this side to the side is cosine, so this would be n cosine of theta j. So now the force of gravity is going straight down. We know that that's evaluated to be mass times gravitational acceleration, g, which is 9.8 meters per second. So, but it's going down, so it's minus mgj. Now, what's the direction of the acceleration? Acceleration is, let me draw a little diagram over here. So the acceleration is going this way, and this is along the incline. Ooh, bad diagram. So this angle, if this is the parallel, is this. So we can break it apart into two components. The down component, the acceleration vector. If this is a, the magnitude, this down vector should be, well actually let's do the right component, the I component. So the I component would be a cosine theta, but it's going down for the vertical component, so that's minus a sine of theta j. You have to get used to like breaking things up into components. Now I'm going to substitute these three equations into our sigma f equals ma, second law, and let's do that now. So n plus fg is equal to ma, so that would be n sine of theta I, I'm just copying it, plus n cosine of theta j, plus force of gravity, which in this case happens to be minus mgj, is equal to mass times acceleration of m times a cosine theta I minus a sine theta j. So let's break it apart into components. So here's the I component for the first one, which says that this is n sine of theta plus the j component, which is n cosine theta minus mg, is equal to the I component, which is ma cosine of theta plus the j component, which is, actually, I put minus, it doesn't matter, minus ma sine of theta. Okay? Ugh. Getting a stiff neck there. Anyway, so here's your I component. So you have a vector. It's got an I and j component. This has got an I and j component. If the two vectors are the same, it must mean that the individual components of each of the I and j's must be equal together. So we have an equation, first equation, the I components means that this is n sine of theta is equal to ma cosine of theta for here. Next, the j component, which is n cosine of theta minus mg, is equal to minus ma sine of theta. So we have two equations, and we don't know what n and a are, but we only require a. So both n and a are unknown. Now to solve for a, or n, I'm going to substitute. Notice that we can solve this. Actually, there's a really fast way of solving this, but it requires you an understanding of matrices. So I'm not assuming you understand matrices, but we can actually solve it very quickly doing matrices. But let's not do it that way. Let's actually solve for n and substitute the second equation. So in this case, it would be n is equal to, from the first equation, that would be ma cosine of theta divisible by sine of theta. So this is n. I still don't know what a is, so I'm going to substitute in the second equation. And so we should now have this into n. So that would be ma, so I'm kind of doing two steps at the same time. So if I substitute here, there'll be cosine squared, sine theta, I'm sorry. And then I move this to this side, which is plus ma sine of theta, and that's equal to mg. So I move this to this side, this to this side, and I substituted for ma cosine theta. So I'll get ma cosine squared sine theta, ma sine theta. Let's just double check I didn't make a mistake. Yeah, looks good. So let's factor out, we can actually factor out the m's, so drop the m's. So that's gone. And we can pull out, so here is a, parentheses, cosine squared theta over sine of theta plus sine of theta is equal to g. And what I'm going to do is find, you'll actually notice there's a sine, I can actually, sine theta is really sine squared theta over sine of theta. And so I'll write this in terms of saying this is really cosine squared theta over sine of theta is equal to g. I'm going to multiply by sine of theta and solve for a and divide. Now, hopefully you remember that trigonometric identity that says cosine squared plus sine squared of anything of the same angle is equal to 1. So we can actually write the final equation as saying this is really AG sine of theta. So we're done. Now if we need to go back and solve for the normal vector, if you wanted to find the normal force that's pushing up on a diagonal, of course, it's perpendicular, then we can back substitute this answer into here. And let me do that anyway since I just need to find the acceleration, but let's do the normal anyway just because we can. So substituting g sine theta into here, we'll get that the normal force is nothing more than m. A is g sine theta, so I'll put the g, and then sine theta cosine of theta all over sine of theta. So I'll just substitute mg sine theta. Now if you notice the sine theta and sine theta cancels, and so we're left with a normal force of mg cosine of theta. Now a quick cursory glance, right, to make sure the units are correct. And that's the easiest thing you can do in double checking your answers. The acceleration, it's in meters per second squared. Sine theta is unitless, so acceleration, yes, units are okay. Look at mass times gravity, that's in newtons, and cosine theta is unitless, so the units are okay. Let's double check. Now we should also check, like we can change the angles in our head, right? So if theta is equal to 0, what would the acceleration be? Well, the acceleration, hopefully, right, would be not moving 0. So let's double check. Sine of 0, acceleration, that's 0, that's correct. And cosine of 0, if it's 1, 1 times mg is equal to n. So yes, if theta is equal to 0, it makes sense. But let's go to the extreme case when theta is pi over 2, or 90 degrees. If it's 90 degrees, then the acceleration should be g. Let's double check. Sine of 90 degrees is 1, so g. So yes, acceleration is going straight down 90. mg's cosine of 90 degrees. Cosine of 90 degrees is 0, 0. So the normal force, there is no normal force if it's straight falling because there's no push on the surface. The surface is not pushing on the object. So the equation seems okay. So now that we know that roughly that our equations seem to be okay, we can do our calculation. What's the acceleration? Last step, substitute. So you'd say acceleration is 9.8 meters per second squared times cosine of 30 degrees? Yes, it's cosine 30 degrees. Hopefully you remember what cosine of 30 degrees is from your equilateral triangles, but I'll just, well, whatever. You basically plug in this number into your calculator and you get yourself an answer. So anyway, the basic procedure, you're going to keep repeating and repeating. Draw a diagram. Do a free body diagram. Make sure your I and j components are labeled so that you can write sigma f, and then after writing this, you can actually break up everything into your components based on your I, j unit vectors. Once you've done that, substitute your vectors into your sigma f equals ma, this equation. And so we get this. Now we just equate the components together, and we get two equations with two unknowns, both the n and a. So then we solve. Once we solve, then we get ourselves an answer for acceleration and n. And basically the same principle for n. Hopefully you're going to be following the same procedure over and over again for all of your Newton equation problems.